Okay, so I'll remind you, what a Markov chain is, because it was a week ago. Markov chain, in a certain sense, is kind of like a memoryless type of thing, in that you're imagining that this particle bouncing around from state to state, and it doesn't remember how it got. It's memoryless not in quite the same sense as the exponential, but it's memoryless in the sense that it doesn't remember or care how it got to the state it's in, right? It's only just like, the only information you need is what the current state is, as far as, right? So it's this conditional independence thing. Given the present, that is what state it's at now, the future and the past are conditionally independent, right? So it's the conditional independence property. And it helps to really just think about pictures. So I'm going to draw just several simple pictures of Markov chains, and we can kind of like just stare at the pictures for a while and try to get some intuition for how these chains behave. And then we'll talk about a few new concepts, and then the most important thing is stationary distributions, going through some of those properties. But there are a few other concepts that we can see pretty easily just by looking at some pictures. Okay, so I'm just going to draw a few pictures of chains. Here's a pretty nice one. So I'll just call the states 1, 2, 3, and there are many examples I could draw that would be nice, and I'll explain what I mean by nice when we get there. But first, let's just draw a few pictures. So suppose you can go from 1 to 2. You're just wandering around from state to state, right? Now, that's a Markov chain. You can picture it this way, like we were doing last time. Just draw states and arrows. And I could put different probabilities on these arrows if I want, but just for simplicity, let's assume that from any state, you look at all of the possible arrows and then put make equally likely to follow a random arrow or something like that. We could put different probabilities if we want. So let's say from 1 we can stay at 1, or we can go to 2. From 2. Have to go to 3. From 3, you can go back to 2 or back to 1, for example, or even just stay at 3. These loops are optional, just for illustrative. I mean, it would be a different chain if I got rid of this, but for what I'm trying to say right now, it doesn't have to be this particular one. Okay, so in a certain sense, this would be a pretty nice one, and I'll say what that means. And then so that's chain number 1. And then let's do kind of a nastier chain in a certain sense. So we could have something that looks kind of similar, 1, 2, 3, and maybe it has these back and forth things, and maybe it has some loops like that. But there are also states 4, 5, 6 down here. And the thing that's, maybe it looks similar like that. You can just, without having studied much about Markov chains or a lot of technical stuff, you can see that there's something kind of annoying about this chain, right? You could never get from state 1, 2, or 3 down here, and from here you could never get back up. Okay, so there's something kind of annoying about that chain. And let's do a couple more quick examples. What if we had a chain that looked like this? This one, usually we number the states 1 to m, but there's no particular reason you have to do it that way. So sometimes it's more convenient to start at 0. And they don't actually have to be labeled by integers either. What matters is not the name of the states so much for what we're talking about now. Anyway, suppose we could go from state 0 to 1, let's say to 2 to, let's say, 3. And you can always go back and forth one step. Except I didn't draw it the way I wanted. I don't want an arrow there, and I don't want an arrow there. So from state 1, it can either go to 0 or 2. From 2, it can go to 1 or 3. At 0, though, it just stays at 0, and at 3, it stays at 3. You can see there's also something kind of annoying about this chain, right? Because if it ever lands in state 0, then it's just going to stay there forever. If it ever lands in state 3, it's going to stay there forever. Okay, and one more simple picture of a chain just to stare at for a while would be, what if the chain looked like this? So from state 1, it has to go to state 2. From state 2, it has to go to state 3. Then it has to go back to state 1. Well, this is a very simple chain to see what's going to happen. It's just going to go around and around and around and around like a clock. So in a sense, we don't need to do any math. I mean, we already know perfectly how this is going to behave. But it's kind of annoying that it's just going around and around and around like that, deterministically. So basically, we want to find ways to rule things like that out. So these three all have kind of annoying properties that we'll mention. This is an example of a nice one. There are many nice ones. Okay, so we need a couple definitions. So the chain is irreducible. I think connected would have been a better term than irreducible, but that's standard terminology. Irreducible means you can get from anywhere to anywhere. So if it's possible, by possible, I mean with positive probability to get from anywhere in the chain. In some, not necessarily in one step, but in some finite number of steps. From anywhere to anywhere. Okay, so just looking at these pictures, clearly this one is irreducible because you can get from anywhere to anywhere. This one's irreducible, and these two are not. You can get from state 1 to state 0, but you can't get from state 0 to state 1. Once you're at state 0, it's trapped. So these two may as well write, I'll just write irreducible, IRR, reducible. This one is reducible, this one is reducible, and this one is irreducible. Red stands for reducible, just for right now. Okay, so that you can just see just by looking at the pictures, right? Now, reducible chains are kind of annoying, just as you can see intuitively like this. On the other hand, it's not that big a deal because if you happen to have a reducible chain, you can always split it up into irreducible components and then just study those irreducible components and try to put them back together. So this reducible chain, I can think of that as kind of two separate Markov chains, right? I could just study this thing up here and this one down here, which I happened to draw with the same structure, but it didn't have to be the same. I just drew that as an example. So I could study this chain on 1, 2, 3 and this one on 4, 5, 6. It'd just be a separate thing, right? Because if you start out up here, then you're just up here forever, and states 4, 5, and 6 are completely irrelevant. Okay, so for the most part, we only need to look at irreducible chains. Okay, just another couple quick definitions. A state, so we're not talking about the whole, this is for the whole chain that you can get from anywhere to anywhere, from any state to any state. Now we're talking about one particular state within the chain, and it's called recurrent if it's true that if the chain starts in that state, it's guaranteed to come back. So if starting there, chain has probability 1 of returning to that state. So it's kind of like certain tourist agencies for certain cities like to say, if you visit our city, then you're always going to keep coming back, right? That's what recurrent, right? It keeps recurring over and over again with probability 1. That is, there can't even be a 0.001 chance that you will not come back to that state, okay? And otherwise, it's called transient. So transient is just the opposite of recurrent. Okay, so that's pretty intuitive terminology. Irreducible is kind of a strange word, I think, but recurrent and transient is pretty natural terminology. And so just to see in this picture, intuitively, all of these states are recurrent, right, in this first picture. Because if you start out at state 2, and then, it's always going to go to state 3, and then maybe it'll go to state 1 for a while, and maybe it'll stay at state 1 for 1,000,000 years, but eventually it's going to go back there, right? That's probability 1, right? It's kind of like, Murphy's Law. Anything that can go wrong will go wrong. I see this as kind of the generalization of, the probabilistic generalization of Murphy's Law. It's basically that anything that happens with positive probability will happen eventually, right? That's true within the finite. So we're assuming a finite number of states here. Different things can happen with an infinite number of states. But with a finite number of states, then even if it's extremely unlikely, it's like extremely, if you start out here, in this example, it's not difficult, but you can imagine a larger example where if you start at state 2 and it's like extremely difficult to get back, right? But as long as it's possible, eventually it's going to happen. So actually, in the irreducible case, for if there's a finite number of states, all of the states are going to be recurrent anyway, because you just wait long enough and it's going to happen. So in this example here, all of the states are recurrent because even though we can't get from state 1 to state 4, this says if we start out at a certain state. So if we start out at state 4, then the chain is just going to be down here forever, right? And so it will visit 4 over and over again. Oh, by the way, I said that it will return, probability 1 of returning to that state once. But if that's true with probability 1, then I can also say with probability 1 that it will return infinitely many times, right? If it's going to return once with probability 1, but then once it's back there, and you could say, well, what if the probability of the second return somehow decreased and it got less and less likely each time? Then it would not be a Markov chain, right? Because once, like let's say you start at state 4, wander around, get back to state 4. Since it's Markov, then you no longer care about that whole past history, right? It's the same problem again. So with probability 1, it's going to come back again. And then with probability 1, it's going to come back again. So if it's recurrent, it's going to come back infinitely often. On the other hand, if it's transient, then it might, come back again and again for a while, but eventually it will stop, and then it will never go back again. Okay? So let's modify, I don't want to draw a whole new picture to this, but let's modify this one slightly, but actually an important modification. If we add an extra edge, let's say from state 3 to state 6, okay? So suppose now that we have that edge, it's still not irreducible because you still can't get from state 4 back to state 1, for example. So it's not irreducible. But now states 1, 2, and 3 have become transient because if you just imagine what this would look like, if you start out at state 1, 2, or 3, it may wander around up here for years and years. Eventually, though, it's going to cross this arrow here. Then there's no turning back, right? And then the rest of its infinite life is going to be here in 4, 5, and 6. It will never go back. It can't. So if I added this edge here, these 3 states would be transient. These 3 would be recurrent, right? Okay. So that should make sense, just intuitively thinking about how would it behave. Let's think about this one here. State 1 and 2, let's think about whether they're recurrent or transient. Well, let's suppose it starts out at state 2, and maybe it wanders around between 1 and 2 for a while. Eventually, though, it's going to hit state 0 or it's going to hit state 3. Once it's in state 0 or state 3, it's trapped forever. Okay? That's called an absorbing state. And this one is absorbing. So it just gets trapped there forever, like a black hole. Therefore, states 1 and 2 are transient, states 0 and 3 are recurrent, because if you start in state 0, well, then you're in state 0 forever, so it's clearly recurrent. By the way, this example is really just the gambler's ruin, just drawn as a Markov chain, right? So this is just, we're studying, of course I could have had more intermediate states here. That's just the gambler's ruin problem visualized as a Markov chain. We're just saying how much money does gambler A have at a certain time, and wanders around at some point, and then eventually ends with either gambler A is bankrupt and then stays bankrupt forever in that problem, or gambler A has all the money, gambler B is bankrupt, and then it stays that way forever. Okay, that's just a visualization of a gambler's ruin. Okay, so this one, everything is recurrent, okay? But it still has this kind of periodicity. So this one would be called a periodic chain. because, for example, let's say it starts here at time, let's index time, so this is time. At time 1, it's here. At time 2, 3, 4, 5, time 6, 7, 8, 9, and so on. So notice that if I index it that way, at times that are multiples of 3, it's always in state 3, okay? Whereas, so then it's like completely predictable at what it's going to do for this example. So we want to exclude things like that. Okay, so those are just some examples to keep in mind, pictures. The nicest one is this one where it's irreducible and all the states are recurrent. For this one, if we also added some way to get from here back up to here, then it becomes a nice one also. It'll be irreducible, everything will be recurrent. But if we can only go one way, then that's kind of a bad one, okay? That would be reducible. All right, so, okay, now we can talk about stationary distributions. So we talked very briefly about them last time, but I'll remind you the definition. S, which is a probability vector, you can just think of that as a PMF, just written out as, I'll say, probability row vector, because it's written out as a row. Just think of that as the PMF, just written out as a row. And it's called a stationary distribution for the particular chain that we're studying. So chain with transition matrix Q, just the notation we were using last time, that's just the big matrix of the probabilities of going from one state to another one. So the definition of stationarity is that S times Q equals S. And from last time we showed that if you start out, like pick a random state that's distributed according to S, where S is not necessarily stationary yet, and then if you multiply by Q, that says what's the probability distribution over states one step later, right? So we're thinking that we're picking a random state according to S, let the chain evolve one step, and then this will be the distribution after one step. And if we want 2 steps, we would do SQ squared, and if we want 3 steps, we do SQ cubed, and so on. So powers of Q are telling us the higher transitions, like the probability of going from state I to J in some certain number of steps. We talked about that last time. But if SQ is just collapses back down to S, that's why it's called stationary, because that's saying that if the chain starts out with the stationary distribution, then it's going to have the stationary distribution at the next step, and then the next step, and so on, so forever. Okay, so for those of you who've done eigenvalues and eigenvectors, you can just interpret this as an eigenvalue-eigenvector equation, which in general might be very, if this is very large, like large number of states, this may be a computationally very intensive, problem to do all the matrix calculations, even with the computer, maybe too computationally intensive, depending on the size of the problem. But anyway, I mean, in principle, all you have to do to solve for a stationary distribution is to solve, this is just a system of linear equations, right? It's written in matrix form, but in principle, you could write everything out as just a linear system, and you just do your usual thing, eliminate variables one by one, or Gaussian elimination or whatever, and solve the system. Okay, well, of course, there are questions which I asked at the very end last time, but didn't answer in detail. It's just like, can we solve this, right? Is it unique, and so on. Okay, so I'm going to state these as theorems. To prove these would involve a lot more linear algebra than I want to get into, a lot more matrices. Some of this stuff follows from theorems in linear algebra that should, in principle, be taught in every linear algebra course, but in practice do not get taught, which would mean a pretty large detour into linear algebra if we want to prove these. But at least we'll state the theorems, and I'll explain what they mean. So just the kind of basic theorems about stationary distributions. Okay, so for any, well, we want the chain to be irreducible to avoid kind of these annoying reducible chains. So for any irreducible Markov chain, and we're always assuming finitely many states, and I won't necessarily always say that explicitly, but I'll just remind you here, finitely many states, because different things can happen with infinitely many states. Then, okay, and we want to know some basic facts about stationary distributions. First of all, a stationary distribution exists. I'll just say a stationary distribution S. Doesn't matter what you call it. But I'm calling it S for stationary. Stationary distribution exists. That's always true. So you can solve this system. And in particular, I mean, you know, when you solve this thing, it would be if you got a solution that had some positive elements and some negative elements, that would be kind of bad, right? But if everything is positive, or if everything is negative, then you could just renormalize it so that, you know, the entries are non-negative and add up to 1. And you can always do that. Secondly, it's unique. So there exists a unique stationary distribution. That's you know, even if there are a trillion states. Thirdly, there's actually a formula in a sense that's kind of interesting in giving more intuition for what the stationary distribution does, and that's that SI equals 1 over Ri, where Ri is the average time it takes to return to state I, starting at state I. So Ri is an expected value. It says if you start the chain at state I and let it run, since it's irreducible, and in the finite case, that also means it's recurrent, so eventually it's going to come back to state I, and you want to know how long does it take. On average, I mean, by definition, that's Ri, and that's reciprocal to the stationary distribution. So I'll just say that's the average return time. That is, how many steps does it take to return to I if the chain starts at I? So I don't think this is obvious that these should be equal. I think it makes sense intuitively that these should be inversely related, right? Because the one way to think of a stationary distribution intuitively is that it's going to be the long run fraction of time of being in a certain state. So SI, to interpret this intuitively, think of that as you run the chain for a long time, and then you say, what fraction of times what was it inhabiting state I, right? That's going to converge to SI, you know, under some mild conditions. So this is the long run fraction of time at state I, and so, like, you know, if the chain is at I 1/10 of the time in the long run, what this is saying is, if you start at state I, then on average it'll take 10 steps to get back to state I. So it's kind of neat that there's just this very simple relationship between these things. And then the last thing is convergence. That is, how do we know that what I just said about the long run, that S is supposed to be like the long run fraction of time in a certain state, and how do we know the other thing? Like stationary distribution is also called equilibrium or steady state, and all these terms from physics or econ that are saying it's something to do with long run behavior, right? So to state that, if there's no periodicity, what we need to rule out is just this periodic case. These first three things are true even for that periodic case. Then we'd only assume irreducible. But if we also assume that there's no periodicity problem, and there are different ways to get rid of periodicity. One simple way is just to say if q to the m is strictly positive for some m. That also implies irreducibility. Because remember, q to the m is the m-step transition probabilities probability of going from somewhere to somewhere in exactly m steps. Okay, so if you write out the transition matrix for this example, it's just 3 by 3 matrix that you can write down easily, and you start taking powers of that matrix, what you'll see is that you kind of have annoying, like zeros show up in some places, and then you take another power and the zeros move, and the zeros kind of oscillate back and forth where the zeros are. But you can never find one power of the transition matrix here where all the entries are positive. Okay? But if it is true that we can find one value of m such that we don't have any zeros in this matrix, that will rule out any kind of periodicity problem. And in that case, then we can just say that we do have convergence. So I'll just say this as the probability that xn, where xn is the chain, converges to Si as n goes to infinity. No matter what the starting, xn is the state of the Markov chain at time n. No matter what the starting state, so we could say start out deterministically, like start at state 1 always. Or we could say we choose a random state according to some distribution, which may or may not be the stationary distribution. You just have to give it some initial condition. But no matter what the initial condition is, in the long run, as n goes to infinity, the distribution, right, that's just the PMF at time n, converges to the stationary distribution. In matrix terms, another way to say that would be just that tq to the n converges. So last time we showed that if we start out, so t is just any probability vector, not necessarily the stationary one. So think of t as just like initially we choose a random state with probabilities given by t. If we want to be deterministic, then just make t have a 1 and everything else zeros. So this would just be the, we showed last time that if we, this is our starting probability vector. Each time you multiply by q, that's just going one step forward in time for the probabilities. This is saying go n steps forward in time, but that's going to converge to the stationary distribution, so that this converges to S as n goes to infinity. So t could be any probability vector, right? Because that's just saying you can start out the chain however you want, then let long time elapse, and it converges to the stationary distribution. Okay, so this theorem tells us, stationary distribution is a very important thing to look at, right? Because it's capturing the long-run behavior. It's also capturing, 1 over, expected time to return to a certain state. It exists. It's unique. So it's very, very nice. The only difficulty with this theorem, really is that it doesn't give us much of a clue for how to compute it. Now you could say, well, we can use this to compute it, but then we have to find Ri, which is also a difficult problem. Okay, so this is a great result, a great theorem, but how do we actually compute the stationary distribution, assuming we do not want to spend the rest of our life doing matrix algebra on SQ equals S? Okay, so there's one especially nice class of Markov chains where the computations are really, really nice. That is, we can get the stationary distribution quickly and easily. Not necessarily easily, in the sense that it may be hard, but it's the good kind. By good kind, it means it may be difficult, but you think about it and you figure it out. But it's not tedious. So I like that more. So that type of chain is called reversible. So I'll tell you what that word means, and then I'll show you how do we find the stationary distributions in the case of a reversible Markov chain. So the reversible chains, just in general, are much nicer and easier to work with than non-reversible chains. So here's the definition. So a chain, Markov chain, with transition matrix that we've been writing Q, Q, and let's say individual elements of Q are just written as Qij, that's row I, column J, okay, is called reversible if there is a probability vector S such that here's the key equation of reversibility. Si Qij equals Sj Qji. And it's kind of a cute looking equation, very useful if this holds for all states I and j. Okay, so look, to get from the left-hand side to the right-hand side, we just kind of swapped the i's. We just interchanged I and j. This became that. So for any particular Markov chain, you know, it may or may not be true that you could find such an S. Okay, and this doesn't tell us how to find S either. But if you assume for the moment that this equation holds, then S is stationary. That's why I called it S. So if I'll just say if reversible with respect to S, that is, if this equation holds with respect to that particular S, then that S is stationary. So if you're lucky enough to have this equation, then you've essentially bypassed doing all, like, you know, solving matrix equations and Gaussian elimination and stuff, because once this holds, we know we have the stationary distribution. We're going to prove that in a minute. Of course, you could say, how do we come up with S in the first place? At least for solving this matrix system, you know, there's a well-known system for doing that you do in an algebra class, that, you know, just solving this linear system, whereas here we have to, you know, cleverly come up with S. So it may take more thought, but you get nicer results, more insight. And for example, a lot of times you can prove something for all, you know, you could have Markov chains that have, you know, n states where you're not specifying n, and then, or m states where you're not specifying m, and then you in some cases you can still solve this thing even without explicitly knowing what the size of the space is. Things like that. Okay, so let me tell you just a little bit about the intuition, why this is called reversible. Then we'll show that this implies stationarity. Then we'll do an example. Okay, so for the intuition, reversible is also called time reversible. This reversibility refers to time. What it says is that if you start out the chain with distribution S, and then imagine like recording a video of, like, you know, you know, imagine one of these pictures, one of these chains, and you're kind of videotaping this particle that's wandering around, you know, in this process. Okay, reversibility says that if you then took that tape and played it backwards in time, right, you reversed it, and you showed that to someone else, they would not know whether it was going forwards or backwards in time. It looks the same. So this is saying that if you run time forwards or backwards, it looks the same. And you can check that, you know, basically using definition of conditional probability and Bayes' rule, that's what this corresponds to. So this is also pretty important in physics too, right? In physics, they like to talk about, you know, whether the laws of physics are, you know, time reversible and things like that. Very important in thermodynamics, stuff like that. But anyway, that's what this means intuitively. And oh yeah, I should also mention that in physics, this is also called detailed balance, which you don't need to know, but in case you ever come across that term, that's just a synonym. Detailed balance is reversibility, but I like the term reversibility more. All right, so let's show that if this is true, then in fact S is stationary. Okay, so it's a quick proof, and it's good practice with this concept. So, suppose that SIQIJ equals SJQJI for all ij. So we've found this S that makes it reversible. We want to show that, in fact, S is stationary. So we want to show that S times Q equals S. That's the definition of a stationary distribution. Okay? All we have to do is sum up both sides. Take this equation. This is for all ij, for all states I and j. So just sum both sides, sum over all I. So I'm summing over all states I. I'm just writing sum over I, but the indexing is that we're summing over all the states of the chain. So the sum of Si Qij equals the sum of Sj Qji, because those are equal, and just so the sums are equal. But now, this is actually very easy at this point, because Sj doesn't depend on I, so we can take that out of the sum. So this is just Sj times the sum over I of Qji. But if you think about what that means, that's the probability of going from state j to state I, summed over all states I. That sum is just 1, because it has to go somewhere, right? That's just, remember, each row of Q has to add up to 1, right? It has to go from j to somewhere. So that's just Sj. Okay, now if you think about what this equation means in terms of matrices, this says to take, or look at this one, we're taking S and we're writing it out as a row like this, S1, 2, blah, 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 Sm, and we're multiplying by Q. How do we actually do that? Well, we just do the dot product, right? This time, and we take a column here and we go this times this plus this times, right? Just matrix multiplication. And what you get then is just for the jth entry, it's exactly this sum, just definition of matrix multiplication at this point. So SQ equals S. That's just the definition of matrix multiplication. Okay, so reversibility implies stationarity. Okay, I mean, that's all, well and good, but are there any interesting examples where we can actually do this? And, there are a couple in the handout. I'll talk about the one that's like the most important one and the most interesting one, I think, we'll talk about now. So, example of a reversible Markov chain would be a random walk on an undirected network. This is a very general, very general example. So you can think of lots of problems that you could encode into this format on an undirected. I'm saying, so far, you had a couple homework problems about networks or graphs, right? And we've just been looking at undirected ones, that is, the edges aren't arrows, that they're actually two-way streets, not one-way streets. But for emphasis, I'm going to say undirected here. Any Markov chain at all, you can think of that as a random walk on some directed network, like any of these, right? Each state, think of that as a node, and we have nodes, and we have directed edges, which are arrows. And if we want to be more general than these examples, we can put different probabilities, right, on different arrows. Okay, so that's too general, right? Undirected means that we have a picture that looks like, I'm just going to make up an example. So let's say, I'm just drawing some nodes, and I'm going to stick some edges. Let's just do a simple one with, let's say, only four nodes. And suppose that, so I'm not drawing arrows now, I'm just drawing undirected edges. Let's say 1 and 2 are connected, and 3 is connected to everything else. And see if I want any more edges. We can draw any example we want. We'll be able to do any of these very, very quickly. just for illustrative purposes. I'm just drawing one of them. So I think this is a good one. All right, so that's our network. Now, and consider, so our random walk just says, imagine, that you start out at one of these states, and then wherever you are, you look at all your available edges, and you pick one randomly with equal probabilities. Right? So that's a pretty natural, you can think of a lot of different problems that you could express in this format, right? And, okay, so for example, from state 3, there are 3 outgoing edges are the same as incoming edges because it's not directed. From state 3, you can either go here, here, or here, probably 1/3 each. And from state 4, well, you have to go back to state 3. From state 1, you can either go to 2 or 3, and so on. And then just randomly wandering around. That's why it's called random walk on this network. Okay, so that's a Markov chain, right? You can write down the transition matrix if you want, but we want to find the stationary distribution. Clearly, it's irreducible. It would be kind of annoying if we had like node 5 over here that's not connected to anything else. Then that would not be irreducible anymore. But let's assume that the graph is connected. That is, you can get from anywhere to anywhere. Okay, and let's let d sub I be the degree of I. And degree just means the number of edges that are attached there. So for this example, d1 equals 2, because I'm just counting, 1, 2. d2 equals 2. d3 equals 3. And d4 equals 1. Okay, those are just called the degrees, right? Just count the number of choices of path at each node. Okay, now notice that we have the following equation is true. di qij equals dj qji, where q is the transition matrix. So let's check. I'm claiming this is true, but let's check why this is true for all ij. Oh, by the way, I drew this without loops. That is, I don't want edges like from one to itself. You can generalize, extend this to handle loops if you want. But right now, I'm assuming there are not these loops. An edge from a node to itself. Okay, so to show that this equation is true, well, if I equals j, then it just says di qii equals di qi. That's always true, so nothing to check. So we can assume I not equal j. Okay, so I'm just going to prove this equation. So let's assume that I is not equal to j. Then let's just think about what does qij look like. First of all, qij and qji are either both 0 or both non-zero, right? That's where this key undirected property comes into play. If we had an arrow here that said you can go from 3 to 2, but you can't go from 2 back to 3, what I wrote would not be true anymore, right? And then you'd have to worry about if one side of the equation is 0 and the other side is non-zero and causes some problems. But in this case, we assume that all of these are two-way streets. So that means, in particular, that means that it's either 0 equals 0, or it's something non-zero equals something non-zero. Well, of course, 0 equals 0 is always true. So we only need to look at the case where both sides are non-zero, right? Now, if there is an edge, ij, so this notation just means if I is connected to j by an edge, like 1, 3 is an edge, then let's just write down a formula for qij. Qij equals, and let's just think about it. What does qij mean? It means that we're at state I, And when we're at state I, we look at all available roads, and we pick one, and we're assuming for now that they're all, it's just randomly pick one, right? So the probability of each particular one is 1 over the degree, right? Because over here there's 2 choices, so it's 1/2, 1/2. So this is just 1 over di. Okay, so in the case where both sides are non-zero, this just becomes di times 1 over di equals dj 1 over dj. That's true, right? That just says 1 equals 1. So because qij is 1 over di in the non-zero case, you plug that in here, then you see that this is always true for all states, which is what we're trying to show. Okay, so notice, just with this one, few lines right here, we derived a result that did not require us to write down any matrices or do any Gaussian elimination and row and column operations and whatever. And it's extremely general because I drew this example with 4 states, but there could be 4 billion states. This is still completely valid, right? Of course, we had some assumptions, which is the most important one being that this is undirected. We could generalize this to the case where we put weights on the edges, and it's a fairly straightforward extension. But the thing that would make things much, much more complicated would be if the weight, or probability of from here to here, if that had a different weight than going back like that. Okay? But you can see, this is extremely general. Let's write down the stationary distribution now. The only problem, so this satisfies this is exactly the reversibility equation, right? Except that di, these are non-negative or positive integers, right? So we just need to normalize it. So to do that, all we have to do is multiply both sides by a constant. This will still be valid if we multiply both sides by a constant, right? So we just need to choose a constant so that we actually get a probability vector. So that just says that in general, let's say we have m nodes, which are labeled 1 through m, and degrees are di, that is the degree of node I. Then just by this equation, it follows that if we take, here's S. We just let Si equal, it's proportional to the degree, right? So it's di divided by the sum of all the degrees. So this j is a dummy variable. We're summing up over all the degrees. So in other words, take the vector of all the degrees and divide by the sum of all the degrees, just to make it add up to 1. Then this is going to be stationary. So we've found the stationary distribution, and it's a pretty intuitive result. It says that the stationary probabilities are proportional to degrees, which kind of makes sense if you're imagining this, in the long run, it's going to be spending more time in the states of higher degree, right? So okay, so that's all for today. See you on Wednesday then.